Hello. Uh, I will try to catch up the course. So today is the numerical method applied in the structure applications. Today I'm going to give a new topic, which is the eigenvalue problems. I think in the structural dynamics you have already learned okay. If we like to solve the the mode shapes of the structures and also the mode frequency of the structures, then we need to solve these equations. The K matrix, which is the one we are familiar with, which is the stiffness matrix, and the U vector, which is the displacement vector. In this vector, it includes all the nodal degrees of freedom. So for different problems, we have different degrees of freedom. For example, if we consider the plane truss problems, then we need to consider the UI and the VI. They are the nodal displacement along the x and along the y directions. If we consider the plane frame problems, then the nodal degrees of freedom will include UI, VI, and the theta I. There are 3 degrees of freedom for each nodal point. Under the M matrix, which is the mass matrix, and we can get the mass matrix. Either you can use the lambda mass method or the consistent mass method. The omega square, they are the natural frequency of the structures. Okay, so if we can solve these problems, then we can get the natural frequencies. Also, we can get the corresponding mode shapes of the structures. Okay, so there are the general eigenvalue problems. Usually we say the general eigenvalue problems, which is okay. So there are 2 matrices. One on the left hand side, the matrix A multiplied by the vector x, which is equal to the lambda bx, and the lambda, they are the eigenvalues. And the x, they are the eigenvector. And they are the eigenvector. If we combine the lambda I and the corresponding eigenvector xi, they will be called the eigenpair. Okay. Next, they are called the general eigenvalue problems. Also, there is a traditional, the standard. This is that's called the standard eigenvalue problems. And ax is equal to lambda x. And also it can be written as lambda I x. Okay. So if the right-hand side matrix, the B matrix is the unit matrix, then these problems can be called the standard eigenvalue problems. Okay. Okay. There are many basic theorems which can be used for the eigenvalue problems, but I cannot repeat the derivations or prove those theorems. So you need to review the engineering mathematics. I think almost all the engineering mathematics class will include the eigenvalue problems. However, the important things is if the A matrix is a symmetric matrix, and which is true for the structure analysis problems, since all the stiffness matrix, no matter it is the element stiffness matrix or the global stiffness matrix, we know all the stiffness matrix, they must be the symmetric matrix. If the A matrix is a symmetric matrix, then we can say if the A matrix is the symmetric matrix, then we can prove all the corresponding eigenvalues, they are the real values. Okay, so if the A matrix is n times n, okay, then we can get all the eigenvalues, they are in the real number, they are the real number eigenvalues. And if all the eigenvalues, they are the single solutions. So if we solve the characteristic equations, we can solve the okay, if these equations, it is the characteristic equations, then it means we got n singular solutions. N single root. Then we have n corresponding eigenvectors. And also sometimes it could be the then this one, the lambda I is the double root. If the characteristic, if you saw the for one root, you can get the lambda minus lambda minus lambda I squared. then you can say the lambda I is the double root. Also, we could have the then the lambda j is the triple root. Then the lambda j is the triple root. Okay, so we could have the single root, double root, triple root. Okay, you can etc. You can go on to the for the fourth time of the root. Okay. Okay, also you can prove the for all the single root, you can find a corresponding eigenvector. For the double root, the triple. Okay. For the single root of the problems, you can find the single. The single means the single independent eigenvector. Okay. Although you can find infinity the eigenvector, but sometimes they are proportional to each other. Then you can say there is only one independent eigenvector. And if we have one eigenvector, one eigenvalue, which is the double root, then we can find two corresponding eigenvector. It means we can find two independent eigenvectors. And for the triple root of the eigenvalues, we can find three independent eigenvectors. Okay, so for different case, we can find different number of the eigenvectors. It depends on the characteristic of the eigenvalues. Okay, so remember, if the eigenvalue is the single root, you can find one independent eigenvector. Double root, you can find two independent eigenvectors. Triple, you can find. Okay, so if the A is the n by n, also if the A is the n by n, the B must be n by n also. And the X, which is must be n by 1. Okay, so if the A matrix is a symmetric matrix, then we can guarantee that we can always find n independent eigenvector. If n is symmetric. Okay. Okay, so remember although the eigenvalues, the number of the eigenvalues could be less than the n, since we could have the double roots, triple roots, or etc. But no matter the characteristic of the roots, we can always find n. We can always find n independent eigenvectors. Okay, but sometimes there are two independent eigenvectors they are corresponding to the same eigenvalue. Okay. So remember, if we got the double root eigenvalue, then we have two corresponding independent eigenvectors. Okay, so that's the one of the basic theorem for the eigenvalues and the eigenvectors. Okay, since we can always find n independent eigenvectors, so it means that if the A matrix is a symmetric matrix, then we can always find n independent eigenvectors, and okay, so we can always use the eigenvectors to form a set of the basis vectors. The basis vector, it means for any u which can be expressed as so it means that for any u vector, we can always use the eigenvectors to get a linear combinations of all the eigenvectors. We can use these expressions to express all the n by 1 vectors. Okay, so then we can say the x1, x2 until the xn, they are a set of the basis vectors. Okay, so for the eigenvalue problems, we can always get this one. Okay, so that's another important theorem you must remember for the eigenvalue problems. Okay, so let's say also remember if we calculate the xi transpose A xj, and also we can calculate the if we calculate the xi transpose A xj and the xi transpose B xj, the values will always equal to 0 if I is not same as xj. Okay, so it means that for different eigenvectors, if we multiply the xi transpose A xj, and also we can calculate the xi transpose B xj, they are always equal to zeros. Okay, so for two different eigenvectors, they are orthogonal with respect to the A matrix. Also, they are orthogonal with respect to the B matrix. Okay. Okay, but if the xi and the xj, they are the same eigenvectors, then if we calculate the xi transpose A xj, the value is not equal to 0. Okay. Okay, so that's the eigenvalue problems. Then we can let's talk about how can we solve the eigenvalue problems. The first method is called the Jacobi method. Okay, the Jacobi method. The Jacobi method, the traditional Jacobi method can be used to solve only the standard eigenvalue problems. Okay. So remember the standard eigenvalue problems, it means the right-hand side matrix, the B matrix must be a unit matrix. Okay, that's the standard eigenvalue problems. The Jacobi method, which is the method which can be used to solve the standard eigenvalue problems. So right now we are considering the problems Ax equal to lambda x or lambda I x. Okay, so that's the standard eigenvalue problems. Okay, so for the standard eigenvalue problems, how can we solve the problems? Remember, this course is the numerical method. The numerical method it is different from the mathematical methods. We can use the strong power of the computer. So we will not have to use iterative solution procedure. So we can rely on the calculation power of the computer. So it doesn't matter we need to do a lot of calculations, since it is very easy for the computer to repeat the calculations many times. Okay, so that's the numerical method. So the solution method will be different from the traditional mathematical methods to solve the problems. Okay, for the Jacobi method, we need to search for the First, we need to search for the order of diagonal elements in the A. Also, we will assume A is symmetric. If we assume the A matrix is a symmetric matrix, then even we try to search order of diagonal elements, but if the A matrix is a symmetric matrix, then we can search only the elements on the upper triangle. Then all the 5 diagonal elements we can search only the upper triangle. Okay, so for the symmetric matrix of the if the A matrix is a symmetric matrix, then if we try to search order of diagonal elements, then we can search for the order Aij, which is j is always greater than the I values. So that's the character. If we got a symmetric matrix, then we just search all elements in the upper triangle, the order of diagonal elements, and we need to search all the upper triangle elements and find the Aij with the maximum Okay, so we will compare the values of all the upper triangle elements, and we need to pick out the element which got the maximum absolute value. And let's assume the value is the Aij. The value is the Aij. Okay, so that's the first step. That's the first step we need to do. We need to search for all the octangle elements. If we found the octangle element with the maximum absolute, then what we can do? We will try to multiply T matrix. We will try to multiply a T matrix, and the T matrix the T matrix will put the cosine theta, negative sine theta, cosine theta, and the cosine theta, sine theta, they are in the ith column and the jth column, and these rows they are the ith row and the jth row. Okay. So we will multiply a matrix. In this matrix, all the diagonal elements they are equal to 1, but only for the TII it is the cosine theta, and for the TIJ it is the negative sine theta, and the TJI which is the sine theta, and the TJJ is the cosine theta, and except for the TII and the TJJ, they are the cosine theta. All other diagonal elements, they are equal to 1. And except for the TIJ and the TJI, they are the negative sine theta and the positive sine theta. All other off-diagonal elements, they are equal to 0. Okay, so that's the T matrix. And for this T matrix, sometimes it is called, we like to make a rotation for the AI and the AJ plane, for the XI and the XJ plane. So right now the original two degrees of freedom for the two corresponding elements, they are the Xi and the Xj. So on the Xi and the Xj plane, we can make rotations. And for these rotations, there is a rotation angle. The rotation angle is defined from the original Xi axis rotate to the new Xi prime axis. And also there is a rotation from the original Xj to the new Xj prime. The rotation angle is also equal to the theta. So the theta is if the theta is positive, it means the counterclockwise rotations. However, remember sometimes the xi and the xj, they are the physical meaning of the xi and the xj. Sometimes it is not something related to the length. Sometimes we could have different physical meanings of the xi and the xj. So the angle theta, you can say, we try to use a traditional concept about the rotation angles. And however, that's the rotation angle theta. And we like to multiply T, post-multiply the T matrix, and pre-multiply a T transpose matrix to the original A matrix. Okay, after these rotations, if we multiply the T and the T transpose, one is T transpose pre-multiplied to the A, T matrix post-multiplied to the A matrix. The purpose of these calculations, if we can get, let's say this the A double prime. Okay, then we try to get A double prime ij, also A double prime ji, they are equal to zeros. Okay, so remember what is the aij? The aij is the originally aij is the maximum aij is the maximum absolute. Originally, the aij is the maximum absolute in the A matrix. But if we can make a rotation of this one, we will get the aij double prime will be equal to 0. Okay, so the solution procedure, we first we need to pick out the element with the maximum absolute, and the next step we will try to rotate the two corresponding elements, ai and aj, rotate them into another two values, ai double prime and aj double prime. But for these two elements, the corresponding element must be equal to zeros. Okay, then let's see how can we get the result like this one. Okay, I think I will take a break right now, since the shorter the video, it will be, it means it takes less memory. It will be easier for me to upload the video file, and also I think so I will control the class time to about 30 to 40 minutes. Okay, so it will be different from the classroom class, since I need to upload the file, and also it is there is another restrictions. I cannot take out my memory card, which will be easier for me to transfer the files from the cell phone to the computer. But right now, the new cell phone, I cannot take out the memory card. So if the memory is too large for the video file, then I cannot send the file to the cloud memory, and so I cannot transfer the file from the cell phone to the computer. So that's why I need to control the class time. It is about the 30 to 40 minutes. Okay, so let's take a break here.